So to show the utility of PCA, let's return to the Gala dataset and just perform PCA. So we have gone through a lot of algebra to show how you can do this manually. But of course, in R, you don't have to do any of this manual mucking around with eigenvectors or eigenvalues. You can use just the command printcomp. We'll see there's a number of different commands in R that will perform PCA or PCOA, which is a closely related technique we'll look at in a second. So here, I just say summary printcomp, and I get my first two principal components explain about 97% of the data. So in these 7 columns of data, there's really only somewhere between 2 and 3 independent columns of non-redundant information. You could represent these 7 columns of data with 3 columns of data and recover nearly all of the information on decompression. So the first principal component, if we just take the first principal component and regress it back against each of the individual columns, so here's our 7 columns, we see that elevation and area, which we'll remember are correlated with each other, are well correlated with the first principal component. And the second principal component actually seems to be more related to adjacent and possibly to species than to elevation and area, which the first principal component seems to be tracking. And of course, the two components, when you just multiply them against each other, right, they've been rotated into a space in which they are orthogonal. That's the whole point. That's what we did. So the correlation coefficient between the two principal components themselves is within round-off error of 0. We can always write out the principal components and graph them out. You can graph them in R. You can graph them in your favorite graphing software. So in this case, for printcomp, we just say Gala PCA $scores and write it to a table, and we get a table that shows us the principal components. If we graph them out, we can see that this is a really useful view, right? So it's actually kind of difficult in looking at this 7-dimensional space here to see which are the outliers and what the relationship is between these, right? Our minds don't go to a 7-dimensional space very easily, but now in this new 2-dimensional orthogonal space, which we'll remember these 2 dimensions explain 97% or so of the original data, we can see that there's 2 outliers, right? So Isabel and Fernandinha, these 2 islands, are really distinct from these other islands, and in fact are driving most of the variation along this first principal component. We can see that these 2 are adjacent to each other. They have among the largest areas so Isabella has the largest area, and Fernandina has the 3rd largest area. They're adjacent to each other. So you could start to make an argument that there's maybe something ecologically similar that's happening between these 2 large adjacent islands relative to all of the other data. So again, you can start to instead of dealing with a 7-dimensional data set, you can deal with a 1 or a 2 or maybe a 3-dimensional data set, and are in terms of thinking about narratives of data, our minds are much more able to deal with 1 or 2 or 3 dimensions than with 7 or 10, or in the case of genomics data, sometimes thousands of different dimensions. So when the first axis dominates, when you have these big outliers here, right, you often get this horseshoe effect, and that's described in this paper here and in many other manuscripts as well. And sometimes I think of this as just that the first axis is so much stronger than the second axis, but the requirements, the mathematical requirements of the PCA are that they're orthogonal, and so the first axis sort of has to bend into this horseshoe shape in order to maintain the orthogonality requirement between component 1 and component 2. So it's just something. It doesn't necessarily mean that the PCOA is invalid, but it's something to keep in mind when you are looking at these data. That really, what's happening here is that this first PCOA axis is just completely dominating the second one because of these outlier data. So if we return to our RNA-seq data set from the previous lecture, so remember this is our day 2, week 12, and week 20 E. coli RNA-seq data set that we've described in great detail in previous lectures. We can do PCA on this as well. Now here I actually have to use the command PRCOMP because in this data set there are more rows than samples. That is to say, there's more genes than there are samples. And printcomp actually throws an error when you try to do that. So we use a different library called PRCOMP, which is it's slightly irritating because the syntax of this library is slightly different. So instead of saying scores like we did with printcomp to get the principal components, with PRCOMP, they're called rotations. But again, in cases where you have more more genes or taxa than you have samples, print comp won't work and you have to use the PRCOMP library, but it's much the same idea. So here we just read this table, we normalize the data, we log normalize the data. We'll take a look at this log normalization in more detail in the next slide or two, and then we just graph out the data, graph out these principal components, right? And so when we do this graph, we can see that we see this clustering where day 2 and week 12 and week 18 cluster separately. And actually now we actually see an outlier here in the week 18 samples, and that wasn't immediately obvious when you just inspected the spreadsheet, right? But when we go to this PCA view, we can see that actually we have one sample in our data set that is an outlier. In terms of this normalization that we performed, this is log normalization. The basic idea here, so this is a normalization that my lab tends to use that not very many other people in the literature use. There are all kinds of, as we talked about when we talked about compositionality, there's all kinds of different normalization schemes. This is the one that I like to use, and this tries to count for the to make the pseudo count equally on all the samples. So we can't take the log of 0, so we have to add some value before we log normalize. And so in order to make the pseudo count work equally for all samples, we switch to relative abundance. So each cell in the spreadsheet is changed to relative abundance, and then we multiply by the average number of sequences per sample. So here, this comes out to be the number of reads, the average number of reads after essentially forcing all of the samples to have the same sequencing depth. We add 1 to that and then take the log 10 of that. So that's the normalization scheme that we use. Again, there's many different normalization schemes out there. Almost no matter which normalization scheme you use, reviewers are probably going to ask you to repeat your analysis with some other normalization scheme to make sure it doesn't make a difference. One other subtlety in terms of working with ecological data, and this isn't really ecological data, so this probably wouldn't be appropriate here, but I just wanted to show this. So if you're working with OTUs as opposed to genes, you might want to use a different dissimilarity matrix called the Bray-Curtis matrix. So instead of using a covariance matrix to feed into the PCA, you use some other distance metric. In fact, this one is called Bray-Curtis. It's just counts the number. It essentially takes the ratio of the number of taxa in common between two samples divided by the total number of taxa that's shown in those two samples. So if you have more, in this case genes, but it's usually used on taxa, if you have more genes in common, you get a Bray-Curtis dissimilarity that indicates the two samples are closer. So you can form a symmetrical matrix based on this Bray-Curtis dissimilarity, or indeed any measure that measures the distance between two vectors. And often when you instead of using PCOA, instead of using a covariance matrix, if you use some other measure of dissimilarity, that's often called a PCOA instead of PCA. But the basic math of the eigenvalue decomposition is the same. So this is the syntax we would use to use this Bray-Curtis dissimilarity instead of a covariance matrix. But you can see that, and now of course, because we're using a different library, the PCA components, or in this case PCOA components, are called $CA, $CA, $U instead of scores like they are for print comp, or rotation like they are for PRCOMP. So these different libraries do slightly different things, and they all have different syntax. But you can see that, as is often the case, it doesn't really much matter for our conclusions. We end up with a slightly different rotation here, but we still see the same basic pattern where we have day 2, week 12, and week 18 separate, and a single outlier for week 18. So I hope you've seen from these brief examples that PCA is extremely useful, and it gives us a way to cluster data in a low-dimensional space, even when we're dealing with a high-dimensional data set.